So this video is a quick introduction to the constant acceleration particle model. It basically takes the stuff that we did with constant velocity and extends it the next step. So velocity is the slope of a position time graph. And so we get the velocity is the change in x divided by the change in time. These three equations are all the exact same. And then if you look at the velocity graph, if you have a velocity graph with a slope, acceleration is defined as the change in velocity over time. It's when something is speeding up or slowing down. And so the slope of a velocity time graph will equal acceleration. You'll notice that the formulas between velocity and acceleration look similar, except we have one new one, which is the average velocity formula. And that's just the final velocity plus the initial velocity divided by 2 will be the average. Okay, so those are the basic equations when we're working with the constant acceleration particle model. We also use a bunch of different representations, just like before. We have position time graphs. Whenever we have a position time graph with something undergoing constant acceleration, it's going to end up being a curve. It's going to be generally a parabola anytime an object is speeding up or slowing down. Technically, if it's a constant acceleration, there's kind of only 4 possible curves. You can be speeding up moving forward like this graph shows, or you can speed up in reverse. You can either slow down moving forward, or you can slow down in reverse. And then we also have the velocity time graphs. So the velocity time graphs, over here on the left we have a constant velocity, but over here we have a constant acceleration, a changing velocity. The velocity starts at 0 and ends at 8 meters per second. The nice thing about it is, just like in constant velocity, if I find the area under this line back down to 0, that area will tell me how much the object is displaced. The same thing is true under constant acceleration. So on this one, it's a triangle shape. So if I take the height, which is 8 meters per second, times the base, 8 seconds, times 1/2, I find that this one is traveling at 32 this one traveled 32 meters during those 8 seconds. And then the third type of the next type of representation that we have would be a constant velocity, or a motion map. A regular motion map for constant velocity, each dot represents the location at a different moment in time. And we have to label the first 3 of them. So 0, 2, 4 seconds, that's constant velocity because the dots are evenly spaced. Evenly spaced dots are constant velocity. But if the dots are getting farther apart, or technically closer together, then that could be a constant acceleration. And so these dots, they show that they're getting further and further apart because of a constant acceleration. And the green arrows show the velocity. The velocity starts off small, gets larger, larger, and larger. And some of the activities that we do will be using acceleration vectors. And for the sake of this class, we'll just say that all acceleration arrows that we use will always be the same length, and they'll be used anytime we have a constant acceleration problem. If there's no acceleration, like the constant velocity, then we wouldn't have acceleration arrows. They would just be dots showing the acceleration vectors. Next up, we have, these are the 4 basic types of motion. One thing that I find is it's useful if you write in forward, above 0, the velocity, if it's above 0, it's moving forward. If it's below 0, it's moving in reverse. The other thing is, if the velocity is getting farther from 0, you are speeding up. If it's getting far closer to 0, you're slowing down. So this graph, we call these stacked kinematic graphs, and we show that there's a relationship between the position time, velocity time, and acceleration time. Again, the slope of the velocity graph will give me the accelerations. So this one's going to have a constant positive acceleration. The second graph is going to have a constant negative acceleration. The third graph also has a negative acceleration because the slope of the line is negative. And the fourth graph, we have a constant positive acceleration. Now we said if it's above 0, we're moving forward. This one is going away from 0, so this is speeding up, moving forward. It's going to give us a curve that goes up like that, kind of a parabola shape. This one is going forward, but it's approaching 0 velocity, so this is slowing down going forward. And we're going to get a curve that looks kind of like that. Notice at the end of the curve, this parabola, it's almost flattened out to 0 slope because we have 0 velocity. This one right here, this is speeding up in reverse because it's below 0 and it's moving away from 0. So this velocity graph shows speeding up in reverse. So speeding up in reverse, there's going to be a curve that goes like that. Notice again it starts off flat because the velocity initially is 0. So I should have no slope at the beginning. This last one shows slowing down in reverse. So slowing down in reverse is going to have a steep part at first, and then a flattens out to a negative spot. I like to use what I call a pencil test, and I hold my pencil up to the graph. On this first graph, it starts off with the slope that's 0, so I know my initial velocity is 0. Then later on, I have a slight positive slope if I hold my pencil up next to it, and I have a slight positive velocity. Later on, I have a steeper slope, so I have more positive, and at the very end, I have a ridiculously steep slope, giving me an overall very positive. And so I can figure out what the curve is if I hold a pencil up to these position time graphs, tangent to the line, then I can figure out what the slope is at each moment in time. Okay. This last slide is the summary of it. These are all the possible graphs, basic graphs that we have for constant acceleration. The purple lines show if it's a negative acceleration. The red lines all represent a positive acceleration. The green ones, this green graph right here, goes along with this green graph. Those are both moving forward with a negative acceleration, or slowing down in this case. This one is speeding up in reverse, so it's moving in reverse, or moving towards the negative area, and so that's going below 0. This one right here is slowing down in reverse, so that's moving in reverse or moving towards the negative direction, but it's slowing down because it's approaching 0. And this one shows moving forward. So the green ones show moving forward, the blue ones show moving in reverse. These two graphs both are approaching 0, so these two graphs are slowing down. These two graphs show speeding up. Turns out we only have 2 acceleration graphs. It's either a positive acceleration or a negative acceleration. So this has just been a summary of some of the basic ideas. We're going to be using these graphs more and more, and we're going to get really used to converting back and forth, just like we had with these stacks of kinematic graphs. We're actually going to have an assignment like that in a couple of weeks, where you're just going through and figuring out what are the shapes. Hope you have a great day, and this is the video. I'm sorry it took so long to get produced for you.